Hi, I'm Negar Goli from University of British Columbia, and I'm going to present ReSprop, Reuse-Sparse-Backprop backpropagation. Training deep neural networks is time-consuming. Training includes forward and backward pass, and backward pass takes 70% of training time. In this study, we focus on accelerating backward pass to have a faster training. Assume a normal training with forward and backward pass. In ReSprop, we make the backward pass about 10 times faster and we reduce the training time considerably. The outline of our presentation is as follows. First, the backward pass calculations. Second, motivation and insights. Third, our ReSprop algorithm. And finally, our results. In forward pass, the output is calculated. After finding the loss in backward pass for each layer, the gradient of output, the gradient of weight for updating the weights, and gradient of inputs are calculated. Due to the significant application of CNNs, we focus on CNNs in our study. In CNN's backward pass, two convolutions are running in parallel to find the gradient of weight and gradient of input, and they both use gradient of output in their calculations. At each iteration, these two convolutions are calculated. Let's visualize gradients movement in a simple 3D example. Here we illustrate the first and second iteration gradients movement. As you can see, the changes through y-axis is almost similar in these two iterations. So we thought we can reuse some of the output gradients between iterations. The question is how we want to reuse the gradients. Can we reuse all of the gradients from previous iteration in the current iteration? We find out in this way the network doesn't converge. So we propose another method. Based on an adaptive threshold, we figure out whether a gradient has considerably changed and we need to update it, or we can reuse the previous iteration's value. In this way, we form our hybrid output gradient. So we store the gradients of all samples and then in the next iteration we reuse them to form our hybrid output gradient. In this way we need a huge storage. So instead we just randomly pick a sample and reuse its gradient. In this way we reduce the storage and also the computation overhead in our ReSprop algorithm. Now instead of the original output gradient, we use our hybrid output gradient in the backward pass convolutions. There are two questions here. First, how much we can reuse? We find out that we can reuse about 90% of output gradients with minimal loss in accuracy. The second question is how reusing makes training faster. The answer is our ReSprop algorithm. Let's take another look at our hybrid output gradient. It can be written as previous iteration gradient plus the residuals, which are the differences between current and previous iteration, and it is sparse due to our adaptive threshold. Now we can break the backward pass convolutions into two parts. First part, which reuse gradients, and second part, which use sparse gradients for the expensive backward pass convolutions. In this way, we can have a faster training. So ReSprop has two parts. First, pre-ReSprop, which is minor calculation and adds a small overhead to the forward pass, and second, back-ReSprop, which is sparse convolutions in the backward pass. Let's take a look at this figure which shows our ReSprop algorithm. We store and then reuse a different random gradient at each iteration. We have pre-ReSprop, which can be done in parallel to forward pass. And finally, we have back-ReSprop, which can be up to 90% sparse and makes our training much more faster. Warm-up ReSprop is a variant of ReSprop. In the warm-up ReSprop, in the first few epochs, we linearly increase the reusing percentage till we get to the target reuse percentage. In this way, the network gets adapted to the reusing. The table shows the accuracy results for ImageNet dataset. We can see that at 90% sparsity, WReSprop loses about 1% accuracy. At 90% reusing, ReSprop makes backward pass 9.6 times faster, which leads to 2.7 times faster training. Pre-ReSprop, which is the main calculation overhead of our algorithm, has less than 2% overhead in batch sizes larger than 128. For more details, please read our paper. Thank you.